So this question's on electric cells. It's quite a long question, so we'll go through it in stages. So the first bit, description question, and it asks you to distinguish between an insulator and a conductor. And so 2 marking points here. The first one is to identify, distinguish in terms of delocalized electrons. So a phrase similar to this: a conductor has delocalized electrons that are free to move, and an insulator does not. We'll give you the first marking point. You then need to say something about what happens in a conductor compared to an insulator. And so when a potential difference is put across a conductor, it causes these delocalized electrons to move, and this causes a current. And this doesn't happen in an insulator. So those are the 2 marking points for that one. Moving on to this one, outline what is meant by the internal resistance of a cell. So 2 marking points here. So the first one, some of the energy delivered by a cell is dissipated as heat energy, driving the current through the cell. So I think the main point here is something to do with heat energy lost inside the cell, and possibly an indication of why that is. Well, it's due to the contents of the cell itself. So that's the first marking point. The second one then is how this fits in with EMF and terminal PD. So something along these lines. This lost energy per charge, which is just voltage, is called the loss volts, where the EMF of the cell equals the terminal PD plus the loss volts occurring inside the cell. So that's the first part of the question. It then goes on to looking at a lemon can be used to make an electric cell. And if I just turn over the page, the first part then here is draw a circuit diagram of the experimental arrangement. And the marking points are the voltmeter in parallel and the ammeter in series. So that's relatively straightforward. The next one, show that the potential difference V across the lemon is given by V equals E minus I times small r. It's easy to lose a mark here because most people write that down as an expression. That's okay, it's in your data booklet. But you need this bit as well. You need to state that V equals capital I times capital R. And then substituting that into this expression and rearranging, you get your final answer. So that would be that one. Moving on, it then shows a graph of how V varies with I. And I've already drawn a line of best fit through the points and extrapolated back to the V axis. And the question is, using the graph, estimate the EMF of the lemon cell. Well, in this case, you would write that the EMF is actually equal to the y-axis intercept because it equals the open circuit PD. It equals the PD when there is no current flowing. So that gives you the y-axis intercept, and it's 1.6 volts. Just a note here for the next question that the current is actually measured in milliamps. So we'll look at the next question now. So the next part of the question is determine the internal resistance of the lemon cell. Again, most people can figure out that the internal resistance is equal to the gradient of the graph. That's the first marking point. The second marking point is you need to use a large triangle on your gradient to manipulate the data. But the final thing here is just to be careful that as I said, that the current axis is measured in milliamps. So your answer comes out to about 300 ohms. And the final 2 questions, 2 calculations. So you're told that the lemon cell is used to supply energy, and it requires a current of 6 microamps, and the clock in this case runs for 16 hours. Calculate the charge that flows. And see how all I've done in my way into this question is I've put the symbols next to the values that I either need to calculate or I'm given. And then I can realise straight away that this is the equation I'm going to use, that I equals Q over T. Rearrange that for Q, put the numbers in, but just be aware that I'm converting 16 hours into seconds, and I get my answer at 0.35 coulombs. The final question is, again, let's just have a look at it, calculate the energy transferred by the lemon in these 16 hours. So a couple of ways to do it, but let's start off with what we know. One of the definitions in this topic voltage or potential difference is just the work done per charge. Well, that's just the amount of energy transferred per charge. So rearranging this equation, I get that energy equals voltage times by charge. I know that the voltage from previously is 1.6, that's the EMF of the cell, times by the charge that was transferred in those 16 hours from that question will give me 0.56 joules. I could use this equation. There's one you can probably remember from GCSE. Electrical energy transferred is voltage times current times time. I would get the same answer. Okay.